All right. So counting units. When we talk about different things, we talk about when we're working with this unit. This should be chapter 10. My apologies. When we're looking at this stuff, we're talking about something called a mole. That's what this chapter kind of centers around. And the mole is really valuable in chemistry because we use it to do a lot of our conversions with it. We use it to be able to figure out, like, if we start with this much stuff, how much materials we're going to end with. So that's called stoichiometry. We're going to use it when we're figuring out concentrations. So if you've noticed, like somebody said the other day, they're like, the thing said 1 mHCl on it. This is called molar. That's how concentrated that solution was. So something called molarity, which is something we use to figure out concentration of solutions. We use moles for that. We use moles a lot in chemistry. And so this is like one of those foundational kind of things that we learn this year. The mole is essentially a counting unit. Okay, just like when you have a dozen, you have 12 things. Or sometimes they give you what's called a baker's dozen, which is 13. It's 13 because they usually give you an extra one in case one's bad. Like if you buy ears of corn or something like that, they give you an extra one in case there's like a, mold on it or a worm or something, When you go to, like if I sent you to the copy room to get a thing of paper, that thing of paper, you know how when you get that, it's like this bit thick and 8 by 11. Yeah. That's a ream. That's called a ream of paper. That's 500 sheets of paper. So that's how many sheets are in there. A league is, I gotta remember what a league is. I don't remember. I always have to look that one up.
1,000 leagues to the sea. No. Yes?
No. Miles. It's 3.5 miles. So it's 3.5 miles.
What does that use to measure?
They measure it in navigation, some sort of like, I know that there was like a book, like 20,000 Leagues Under the Sea.
I said that.
So,
technicality.
A gross is 144, which is essentially a dozen. Okay, so that's a gross. A pair is 2. A score, where's a score?
25.
Yeah, 4 scores at 20 years. Yep, 20 years. So it's 20 years. And then in chemistry, we have something called a mole. And a mole is 6.02 times 10 to the 23rd things. Okay, so if you typed that out, that's how many things it would be. Okay, which is a crazy number. So if you think about it, like a dozen paper clips is going to look different than a dozen students, right? But there's still a dozen. So the masses would be different as well. And that's the same idea with like your periodic table. If you have a mole of hydrogen, it's going to be 1 gram. If you have a mole of uranium, it's going to be 238 grams. Okay. If you have a mole of carbon, it's going to be 12 grams. So it just depends on what you're, just like a dozen paper clips is going to look very different than a dozen students. Their masses are going to be different. It's just a counting unit. But every one of these, if we had a sample of each of these, they'd still have that many atoms in each of them. Okay. Well, it's a mole. That's what a mole is. It's just a counting unit. Okay. So if you had 12 grams of carbon, that's how much it would be. I think I've got like a sample in the back where I've got some of these laid out, measured out.
Keeps them just for the same.
Sometimes I remember the score numbers because I didn't watch Abraham Lincoln's Vampire Hunter. That was such a weird movie. Well, it's a really famous book, but the pacing of the movie was just so weird. What happened was they would bring up like conflict and then instantly solve it, and then bring up another conflict and instantly solve it.
Yeah.
And then every like overarching conflict, the second the solution was presented, it was solved. Like,
Yeah, they would, yeah.
it never.
Yeah, I'm not finding it.
There wasn't called Abraham Lincoln's Vampire Hunter. Basically, it's like Lincoln, through his life, but there's vampires.
Okay.
So he fights.
All right, if you go back to your homework from last night and look at those things, if I wanted a mole of magnesium acetate, I would go and measure this much out. If I wanted a mole of water, I'd measure out 18 grams. If I wanted a mole of calcium carbonate, I'd measure out 84.1 grams. So these allow me to measure things in grams.
Is that why it's called molecular mass?
Yep. Well, molecular refers to the fact that these are molecules.
Oh.
Okay.
So do they have to be in like units of moles to be reactant with one another, or is it just the way that it's measured?
It's just a measuring tool. That's all it is. Okay. All right. So mole is abbreviated, and get this, how much this saves you. M-O-L. I know, it's crazy. Sometimes you will see it abbreviated with the letter N.
What?
I don't know why. I can't tell you. It just is. Okay. It's used to measure the amount of matter in a substance. And it's named after Amadeo Avogadro. It's used to count extremely tiny particles such as atoms or molecules. And we get to use our old friend, dimensional analysis. That's why we've been practicing it the last day or so.
Oh, yeah.
All right. So our conversion factor then, for this chapter, you have two conversion factors. This is one of them, right here. And then the other one is the masses off the periodic table. So the masses on periodic table equal 1 mole of that substance. Okay? So this doesn't matter what material this is. It's irrelevant. 3.5 moles of anything will give you the same number of molecules. And that happens to be for this guy. We would set this up. Your moles would cancel. It's going to leave molecules on the top. And there's your answer for that problem. Okay? So the mass in grams of 1 mole of any pure substance is called its molar mass. The molar mass of an element is equal to its atomic mass and has the units of grams per mole. So find manganese on your periodic table. We round to the tenths of place. So manganese is what? 54.9. Wait a minute. That would be, this says 3 moles though. Hold on. Back the train up.
just multiply it by 3?
Yep. So we're going to put this into dimensional analysis so you can get used to putting that where it should be. Okay, my moles go down here, my grams go here. So this is going to be 1 mole, and 54.9 goes here, and then we multiply across. 54. Oops, clear. 54.9. 164.7.
But didn't the moles cancel out?
Yep, they cancel out.
Then why is it grams per?
That's grams of manganese.
No, I'm talking about the molar mass.
Here, well, the molar mass on your periodic table is grams per mole. That's what this is.
Oh.
So this guy here is grams per mole. When you multiply it, the moles are going to cancel because they'll divide out, and that leaves you with grams.
Okay.
All right, making sense?
Mm-hmm.
Okay. So here I've got grams of water. We're going to figure out how many molecules that is. So I've got 1.00 grams of water. I'm going to get rid of grams, and I'm going to go into moles. And then I'm going to go moles into molecules. Write down your path first with your units, and then go back and fill stuff in. When I go grams to moles or moles to grams, that's always going to come from the periodic table. Darn it. So anytime I'm dealing with these grams, that's coming from the periodic table. That conversion factor you get from the periodic table. Anytime you're going moles into molecules or atoms, moles into items, I'm going to put items down here. Sometimes it's atoms, sometimes it's molecules, sometimes it's ions. Anytime you go moles into items, that's going to be your 6.02 number. That's Avogadro's number. I don't like that abbreviation.
So we add up oxygen and hydrogen.
Down for this part right here, yeah. So here, I've got 2 hydrogens. My hydrogens are 1 each, for a total of 2. My oxygens, I have 1 at 16. So that's 16.0. I add those together, that's 18.0.
Then you're disrupting class. Julia!
So the material on the periodic table is grams per mole. So anywhere that I have grams, the 18 goes with the grams, and then this is going to be 1 mole. And then in 1 mole, we know we have 6.02 times 10 to the 23rd molecules. That's Avogadro's number. So we just have 2 conversion factors for the most part in this chapter. Okay? Stuff off the periodic table, get you between grams and moles. And then Avogadro's number will get you between moles and however many items it is.
So we just divide Avogadro's number by 18.
Yeah, this time because it's just 1. Yeah. And you can actually, if you have one of these fancier calculators, there's a store function in here where you can store like Avogadro's number. I could show you how to do that if you want, and then you don't have to type it in every time.
Okay.
sort. Get alpha and then that letter. No, if you want to recall it, just alpha A.
So 3, I ended up with, why is this not, oh, because I still have it on eraser. 3.3, I need 3 sig figs. I need 3 sig figs because this is 3 sig figs here, my measured amount. Remember, these don't count. These are conversion units. They don't count in my significant figures. It's just the measured amount. So 3.34 times 10 to the 22nd molecules. I will get people on the test that write down 3.34. And they'll forget to go back and grab this part. It should be a red flag to you in your brain that if you had a gram of water, you've got more than 3 molecules there. Okay? And think about the size of 3 molecules. Okay? Would you be able to see 3 molecules of water? No. Okay? So think about that before you write down an answer. Okay? Can you see a gram of water?
No.
Yes.
Oh, yeah.
Yeah, you can see a gram of water. It's a milliliter of water. You would be able to see that. Okay? There would be more than 3 molecules in there.
Hopefully.
Okay? So use a little bit of logic when you're coming up with some of these answers. All right. Any questions on that guy? Does he make sense how you do this? Okay. Whoops.
Whoa.
Yeah, come on, go away. Go away.
That always happens.
Go away. Well, it's because I screw up. There we go. All right. Sorry about that. All right. So now we've got moles of zinc, and they want us to convert that into atoms. So see if you can set that up with your dimensional analysis and come up with the answer for that.
Number, and then hit store, which is above the auto, and then it's letter.
I usually use A for Avogadro.
Oh.
I also have like Planck's constant stored in there. I have
Really helpful.
speed of light stored in there so you don't have to retype it all the time. But if it's stuff that you're using a lot, then you don't have to retype it all the time, which is kind of nice. All right, so you should have gotten your moles down here. Should have gotten your atoms here.
Right to the tenths?
It would go to the, you should have 3 sig figs in your answer because you've got 3 sig figs for your measured amount. This is going to be 6.02 times 10 to the 23rd. Remember, conversion factors don't count for sig figs.
Whoa.
So I ended up with 1.51 times 10 to the 24th. Your units are atoms and then zinc. So that's how you would properly label that answer with the correct number of sig figs. All right, when they ask for the formula mass, that's the same as the molecular mass or the molar mass of this guy. So we're going to go for copper, Cu. How many coppers do I have? And the mass on the periodic table for copper is 63.5. Good. I have 1 sulfur. He comes in at 32.1. Good. And my oxygen, I have 4 of those times 16. So I have 64 here. I have 32.1 here. And here, 127. Thank you. All right, then we just add those up. 6, 3, carry the 1, $223.1. Did I do my math right?
Yeah.
Okay, and the units here are grams per mole. That's what your units are on your periodic table, are grams per mole. All right, they've given you the molecular mass here so that you don't have to calculate it. They want to know how many grams you would need to have 8 moles. So we need 8 moles of water. My balance back there doesn't measure moles, it only measures grams. So I need to know how many moles or grams to measure out for that water. What did you get? $144.2 grams per mole. Why did I round this to a 2? Right, I need 4 sig figs because of this, not because of this. This does not count in for sig figs. This is a conversion unit. This is what they measured. Okay, so this is the measured amount. That's what drives my sig figs. All right, we want to figure out how many moles we have in 25.5 grams of silver. Figure out how many moles that is. Where did you finish your 10-1A? Your coloring?
Yeah,
Okay.
yeah, because I didn't have the red. Three sig figs, right?
Yep, 3 sig figs. So I'm going to have grams down here. I'm going to have moles here. This is off periodic table 1079 is here. And this is going to be 1. So 25.5 divided by 1079. I end up with 3 sig figs. So 0.236 moles of Ag. Got that? Cool. All right, next one. We're figuring out atoms in this sample. So we have 55.2 grams of lithium. This is going to be a 2-step conversion process. So you're going to have 2 conversion factors here. Let's see if you can figure out how many atoms of Li you would end up with. Anybody having any trouble with any of these? Getting the right answers. Gonna call me over and let me help you? Anybody? Good. All right. How about the next one? This one, if you're not doing things right in your calculator, this will catch you. You'll end up with the wrong answer here. So if you're having trouble getting the right answer for this guy, and I end up with people every year that have trouble with this one, because they're still doing times 10 to the instead of using that EE key on their calculator. All right, bismuth is 209. All right, how'd you do on that one?
Oh, there's All
Right.
You scared me.
Right. No decimal at the end, because that would give you 466, right? Good. Do that one in your calculator. Make sure, because I want to catch if you're having issues with your calculator. Every year I get people giving me an answer like 10 to the 48th or 10 to the, 47th, something like that. If you're doing this wrong in your calculator, you're going to get 2.09 times 10 to the 48 or 47. So if you got that in your calculator, call me over and let me help you with it. This is a crucial catch because then we can show you how to use your calculator right. Good?
Oh, it was just multiplied by 10, right?
Yeah.
Okay.
Because these end up canceling, they'll divide out, and this will be 10 to the 1 times that, which is, so. Okay. We've got a couple more here to talk about. These are just kind of repetitive of what we've been doing. I want to skip to number 9. That way we have enough time to get number 9 done. And number 9, we've got this guy, okay? And this is going to introduce one more conversion factor in, okay? But your conversion factor is held in this formula. So watch what I'm going to do here with this. So if we're working ahead, kind of pay attention to this guy, okay? Because it's going to be a little bit different from what we were doing. So I've got 6.04 grams. That is Al2. SO43. I'm going to convert this into, I'm going to go into moles here, which is what we were doing. Okay. So I need to figure out that's 54. And I have 3 sulfurs, which would be 96.3. And 12 oxygens, 96. Okay, so 342.3 down here and 1 mole. And then I'm going to go moles into molecules. Okay, and this, at this point, this is nothing that we haven't been practicing. It's the next step that I need you to pay attention to. Okay, so get to this point and then look up so that I can move on to this next section here for you.
Because right now, if we were to do it, it would just be molecules.
Mm-hmm. And they want to know atoms. Okay. Are you good? You got everything written down? Ready for the next step?
Mm-hmm.
Okay. So now they want to know atoms of oxygen. So I'm going to go molecules into atoms. For every one molecule of this, I have how many atoms of oxygen? 12. So do you see how we can get that conversion factor from the formula? Does that make sense? Where I got that from? For every one of these, I have 12 oxygens. So that's where that comes from. And then you just do the problem the way we've been doing them. So multiply across the top, divide by the bottom.
Dividing it by the grams that are in what mixtures?
This is the molar mass off the periodic table. So I took 2 aluminums, I took 3 sulfurs, and I took 12 oxygens and added them together off the periodic
So you
table.
break it down and multiply by 12 because of the oxygen.
Right, because they're asking you how many atoms of oxygen are present. All right, so I ended up with 1 point, how many sig figs? 27 times 10 to the 23rd, and that's going to be atoms of oxygen. Questions about that guy? Is it making sense? All right. Then we did percent comp earlier this year. Yep, we did it back in chapter 3. Okay, it's the percentage by mass of each element in a compound. It was just part of the whole. It can be determined from the molecular formula. And it's always the same regardless of the size, sample size. I guess it should be sample size, sorry. Sample size of the compound. And it was just part over the whole. Okay. Good. Ready to do one sample of that? It'll just take us a second or two. Let's just do this guy real quick here. No, that's not what I want. Percent composition is what I want right here. Okay. So we've got Na. I have 2 of those. I have 1 sulfur. And I have oxygen. I've got 4 of those. Where did I get these values from right here? Periodic table for each element. So sodium was 23, sulfur, oxygen. I'm going to multiply through. This is 46. This is 32.1. This is 64.0. And now I'm going to add them together. 164. So I end up with 142.1. So then if I want to do percent composition, I'm going to take the part divided by the whole times 100. And that's going to give me my percent sodium. Then I'm going to do the same thing. I'm going to repeat with the same thing. I'm going to do my sulfur, which is 32.1 divided by the whole times 100. And that's going to give me my percent sulfur. Do you remember doing these? And then my oxygen, I'm going to do 64.0 divided by 142.0 or 142.1 times 100. And that's going to give me my percent oxygen. So this guy here is going to be 32.4. This will be 45.0. And I'll go back and do my sulfur. I did them out of order because I didn't want to change pen colors. And then this guy ends up being 22.6. What should these values here add up to be?
100%.
Right. Oh, goodness.
Oh.
Wow. That shouldn't have happened. Sorry. Mean to make you sick there. Yeah. So these should all add up to be 100%. Occasionally you'll get 99.9. Sometimes you'll get 100.1, but it'll be right in that ballpark. All right. Tonight you're doing 10-2 for tomorrow, and I think it's 2 pages. So flip the page over. Make sure that there's not another sheet. Okay.
You hear that, Barry? 2 pages.
Thanks for being quiet.
What?
Yes, Ben, I appreciate you playing the sound. Is it worth?
Fix some things we know and then just take me a step further.